In the name of Allah, who is most beneficent and merciful, my name is Umayya. I'm from Chemistry Department and my ID is 04. Today, I'm here to present a practical. And the topic of the practical is study formation of complex ions and behavior of some metal hydroxides. So let's start this practical. This experiment involves the separation and identification of ions using two important reaction types. First is the formation of complex ions, and the second one is the amphoteric behavior of some metal hydroxides. First, I'll discuss about the formation of the complex ions. Although usually cation formulas are written in solution as if they were simple ions, for example, aluminium ions, these ions are actually bound to a number of water molecules arranged around the central ion. The water molecules in this case are examples of a much larger class of molecules and ions called ligands that form coordinate covalent bonds with a central metal cation. And in this diagram you can see that is the bond is of the form lone pair manganese ion, where L has denoted an otherwise unused lone pair of electrons to the electron accepting metal ion. In the water molecule, there are two lone pairs of electrons on the oxygen atom, and either of these may form a coordinate covalent bond with a metal cation. In this diagram, you can see a lone pair of oxygen is being covalent bonded with metallic cation. So ligands are often small polar molecules, for example, water and ammonia, but they can also be anions, for example, chloride ions or hydroxide, etc. The combination of a ligands with a metal cation is often called a coordination complex. If the complex is an ion, it is then called a complex ion. For example, here you can see diamine silver. It is a complex ion, and the complex ion is formed by silver ion and ammonia that dissolve in silver chloride. So formulas and stabilities of complexes vary greatly. Usually complexes involve 4 or 6 ligands arranged at the corners of a tetrahedron or octahedron about a metal cation. And the cation is most often a transition metal ion. However, complexes having other than 4 or 6 ligands are possible, such as the silver ammonia complex. The presence of a transition metal in a complex often leads to highly colored complexes, such as blue copper ammonia complex. This complex is much more stable than the insoluble compound copper hydroxide, for example. So adding excess ammonia to a solution of copper ion leads preferentially to a complex ion. And that complex ion is tetramine complex. Advantages of formation of complexions. Complex ion formation can often be used to advantage in ion separation. If two salts precipitate together, they can sometimes be separated by dissolving one other complex ion formation while the other remains uncomplex. Indeed, this is the way you separated silver from mercury. Just like that, silver chloride dissolved when ammonia was added because the soluble complex ion diamine silver was formed. Now we'll discuss amphoteric metal hydroxides or behavior of amphoteric metal hydroxide, which is the second part of this practical. An amphoteric substance is one that can behave as a base acid and a roasted base. The best examples are formed with metal hydroxides such as aluminum hydroxide and zinc hydroxide. Insoluble aluminum hydroxide can be formed by the addition of hydroxide ion to soluble salt of aluminum ion. And in this equation, you can see the insoluble metal hydroxide can act as a base, and it is acting like an acid when it can react with a base. So both reactions are given. In both cases, it reacts like a base, and in the second case, it reacts like an acid. This aluminum hydroxide is said to be amphoteric. Only certain cations show amphoteric behavior, so this can be exploited in separating cations. If, for example, sodium hydroxide is added in small amounts to solution of iron ions and aluminum ions, both will initially form precipitates: rust-colored iron hydroxide, diamine silver complex ion, and white aluminum hydroxide, because aluminum hydroxide is an amphoteric hydroxide, while iron hydroxide is not. For the treatment with sodium hydroxide, we redissolve aluminum hydroxide and leave iron hydroxide as an insoluble solid. If you then centrifuge the mixture, and you will have separated aluminum ions from iron ions. Experimental procedure. Before beginning this experiment, place the following solutions in the small drop-in bottles in your desk. 6 molar sodium hydroxide, same amount of hydrochloric acid, same amount of ammonia. Labels are available in the laboratory so that you can label the bottles. The observations you make on the known solutions can be entered on the table provided with the experiment. When you have completed the table, tape or staple the table in your laboratory notebook. Tests of the ions to be studied in this experiment are copper ions, nickel ions, and so on. Place a few drops of each known solution in separate small test tubes. And first know the color of each solution. Solutions of transition metal ions in particular are often colored. So this was the practical in which we discussed behavior of some metal hydroxide, and we studied the formation of complex ions. It was all from my side, so thank you.